So yeah, Hello everyone. I am Nancy, and today I will be presenting my project title AI-based food calorie estimation using deep learning. The main idea behind this project is to help people easily estimate the calories in their meals by simply uploading a photo of their food. This system uses artificial intelligence to recognize the type of food and automatically calculate the calorie content. It's a small step toward using technology and to promote healthier eating habits and small nutrition tracking. The challenges of calorie counting. Counting calories manually is something many of us find difficult. You have to look up values online, read food labels, or guess portion sizes, which can be time consuming or inaccurate. So, my motivation for this project was to automate this process using AI to make food calorie estimation fast, reliable, and user friendly. AI in food calorie estimation. AI is the brain of the system. It's act like a small nutrition assistant that can look at your food and tell you its calorie value instantly. This is done through three main technologies: image recognition, data analysis, or machine learning. Image recognition, where AI sees and identified the food. Data analysis, where the system connects visual features with nutritional information. Machine learning, where the model learns from large food data sets to improve over time. So, the AI model first recognizes the food image, then searches its nutrition database to calculate calories, proteins, fats, and carbohydrates. In short, AI builds a bridge between what we see and what we eat, making calorie estimation automatic, accurate, and efficient. Image recognition. The core of the system is image recognition, which allows the AI to see and understand the content of food images. This is achieved using deep learning, specifically MobileNet V2, a CNN that is a great at image classification. CNNs can recognize complex visual patterns such as the color, texture, and shape of different foods. To train this system efficiently, I use transfer learning, which means using a model already trained on millions of foods and adapting it for categories. This saves times, use less computational power, and still gives solid results even with a limited dataset. AI techniques. Several AI and deep learning techniques were applied in this project. Uh, Transfer learning, feature extraction, data augmentation, calorie mapping. Transfer learning, the base layers of MobileNet V2 were kept frozen and new dense layers were trained on food images for classification. Feature extraction. The CNN automatically extracts features like color, texture, and shape to identify food categories. Data augmentation. By rotating, flipping, and scaling images, the dataset diversity was increased. Calorie mapping. Once a food item is recognized, it's mapped to a CSV nutrition file that contains calorie, protein, fat, and carbohydrate values. These steps make the system capable of both recognizing food and estimating its nutritional content. Food calories. Once the model predicts the food type, the next step is calorie estimation. The system uses a calorie lookup table that lists the average calories and nutrients for each food type. For example, pizza about 266 kilocalorie per slice, burger about 295 kilocalories. Uh, After identifying the food, the model fetches these values and displays the estimated calories, proteins, fats, and carbs through the web app. So, with just one photo, users can instantly know what's on their plate in both images and numbers. Deep learning model, the mobile net v2. The main model used in this project is called mobile net v2, a type of convolutional neural network. CNNs are powerful at image classification task. I used a technique called transfer learning where we take a model that's already been trained on a large data set and fine tune it for our specific task. This saves time, resources, and still gives good results for small projects like this. MobileNet V2 was chosen because it's lightweight, fast, and works well for web or mobile applications. Methodology. The project involves four key stages: data preparation, model training, calorie mapping, and deployment. Dataset preparation, I used a subset of the food 101 dataset which has over 1 lakh images of over 101 categories. For this demonstration, I used 20 major food categories such as pizza, burger, pasta, and sushi. The data was split into 80% for training and 20% for validation. Model training, I trained the model using MobileNet V2 for a few epochs. The base layers were kept frozen and new dense layers were added to adapt it to the food dataset. Calorie mapping. Each predicted food class was linked to a calorie lookup CSV file which contained calorie, protein, fats, and carbohydrate values. Deployment. The final trained model was deployed as Streamlit web application, allowing users to upload food image photos and instantly view calorie predictions. Results. Here are my model's training results and evaluation graphs. After multiple epochs, the model achieved accuracy around 5%, top 3 accuracy about 15%, loss 2.99%. Now 5% sounds low, uh, but it's not a mistake or a failure. It's actually expected at this early prototype stage. Let me explain why clearly. The purpose of the project. The main goal was the project to build a complete working pipeline, not just to chase high accuracy. The main idea was to show that AI can successfully perform every step from food recognition to calorie mapping, which the system does perfectly. Limited dataset. Instead of full 1 lakh images, I trained only 20 food classes for demonstration. When a deep learning model gets less data, it naturally performs with lower accuracy. Training dataset. The model was trained for a few epochs on limited hardware, so it I did not have enough time to learn complex features. With longer training and better computing power, this accuracy would easily improve. Real world difficulty. Food recognition is a very complex visual problem. For example, two different curries or salads can look almost identical. Even advanced research models struggle to exceed 80 to 85% without massive data sets. So, while the number is low, what's more important is that the entire systems work end to end. It can take an image, classify the food, and display calorie details, which means the pipeline is successful and functional. Streamlit interface. Here you can see the Streamlit web app I developed. The user can upload or capture an image of a meal, and the app will predict the food name, show the top 3 probable results with confidence scores, and display the estimated calorie content and nutrition breakdown. Even though the prediction confidence is around 5%, the app shows that the model integration works perfectly. From image input to prediction to calorie estimation to visualization. This is exactly I am aimed for, a working proof of concept that can be improved later. Applications in healthcare and diet management. AI based calorie estimation has many real world applications. It helps users and patients track daily calorie intake automatically. It supports weight loss and chronic disease management by monitoring food habits. It offers personalized diet insights for health conscious individuals, and it saves time by eliminating manual data entry. So, this kind of technology can become a digital nutrition assistant for users. Application in industry integration and impact. This technology can also be integrated into food delivery or health tracking apps. For example, Swiggy, Zomato, or Fitbit type apps can use similar AI to display calorie data automatically. AI also help in nutritional labeling, product recommendations, and creating healthier food options. So overall, it supports innovation in the health and food industry. So yeah, future scope. There is a lot of potential to enhance this project further. In the future, I plan to expand the dataset, use the complete full 101 dataset, and add more high quality images for diverse cuisines. Improve model accuracy. Use efficient net or vision transformers, more powerful architectures known for higher accuracy. Enable real-time recognition. Add camera based detection so users can get calorie info directly on their phones. Data enrichment. Include micronutrients and portion based calorie calculations for more personalized tracking. These improvements will help convert the system from a research prototype into a practical real world application. So conclude, this project demonstrates how AI and deep learning can be applied to simplify calorie estimation using just an image. Even though the model accuracy currently stands at 5%, the system achieved several important milestones. It successfully implemented an end-to-end AI workflow. It integrated image recognition with nutritional dataset and It deployed a working web application for user interface interaction. The lower accuracy is not a result of error, but rather a natural outcome of using a smaller data set and limited training resources. With dataset expansion and fine tuning, the performance can significantly improve. This makes the project a strong proof of concept and a foundation for future AI driven nutrition system. Thank you.